Hey everyone, welcome back to the channel. I'm Darshan, and today we're doing something massive. This is the complete Axum Web Framework course from absolute zero to production-ready applications. Axum is the web framework in Rust right now. Built by the Tokio team, it's fast, type-safe, and gorgeous to work with, and if you've been wanting to learn Rust web development, this is your video. We're covering version 0.8.8, the latest release with all the new features. By the end of this video, you'll be able to build production-grade REST APIs, handle authentication, work with databases, WebSockets, and deploy to production. Now, quick heads up, I'm not writing every single line of code from scratch on camera. That would take hours and honestly, you'd fall asleep. Instead, I've built a complete 12-module course project. Each module is a self-contained Rust crate that teaches one topic. The full code is on GitHub, link in the description. What I'm going to do is walk you through each module, explain the concepts, show you the key patterns, and teach you why things work the way they do. Think of this as a guided tour through professional Axum code. You'll learn way more this way. Here's what we're covering in this course: Module 1 through 4, the fundamentals: setting up servers, routing within no path syntax, extractors to get data from requests, and response types. Module 5 through 7, intermediate concept: state management, tower middleware integration, and proper error handling. Module 8 and 9, real-world features: PostgreSQL database integration with SQLx, and JWT authentication with password hashing. Module 10 through 12, advanced stuff: WebSockets, server-sent events, file uploads, testing strategies, and production deployment with graceful shutdown. Whether you're a Rust beginner or coming from other web frameworks, this course has something for you. Before we dive in, subscribe if you haven't, smash that like button, and turn on notifications. I'm releasing Rust content every week. Join our Discord community, link in the description. That's where we help each other debug, share projects, and discuss code. And if this content helps you, consider buying me a coffee. Every coffee funds more tutorials like this. Link is below. Alright, let's build some web servers. Let me show you the project structure first. This is a cargo workspace, a collection of 12 independent Rust crates. At the root, we have the main cargo.toml that defines all the workspace members and shared dependencies. Each module is its own folder with its own cargo.toml and source code. This structure is perfect for learning. You can run any module independently with cargo run-p module 01-intro. Each module focuses on one concept. No confusion, no mixing topics. Before we start coding, let me highlight the big changes in Axum 0.8. This is important because you'll see a lot of outdated tutorials online. First, the path parameter syntax changed. Old code used colon like /users :id. New code uses curly braces like /users open brace id close brace. This is more readable and allows routes that actually start with colons. Second, the async trait macro is gone. Custom extractors no longer need that macro. Rust now supports native async traits. Your code is cleaner. Grgh, the serve function is simplified. No more complex setup. Just create a listener, call Axum serve, and you're running. These aren't minor tweaks, they're significant improvements. Let's see them in action. Looking at our workspace cargo.toml, we have all the essentials. Axum 0.8.8 is the web framework. Tokio 1.42 with the full feature is our async runtime. Serde handles JSON serialization. SQLx connects to PostgreSQL. JSON Web Token and Argon 2 handle authentication. Tower and Tower HTTP provide middleware. Tracing gives us structured logging. All dependencies are defined once at the workspace level. Each module just inherits what it needs. This keeps versions consistent and updates simple. Let's start at the beginning. Module 1 is your hello world moment with Axum. Open module 01.on2/src/main rsers. At the top, we import what we need from Axum: the router for defining routes, the routing module with get and post functions, and the status code enum for HTTP status codes. We also import Tokio's TTP listener because Axum needs a network listener to accept connections. Now, if you're new to Rust, don't worry. I'll explain each piece as we go. The imports might look scary, but they're just bringing tools into scope like imports in Python or includes in C. The main function has the Tokio main attribute. This is crucial. Let me explain why. Axum is async. It uses Rust's async add-to-wait for non-blocking I/O, but async functions can't just run on their own. They need a runtime, something that schedules and executes them. Tokio is that runtime. The Tokio main attribute is magic. It transforms your main function into an async function and wraps it in a Tokio runtime. Without it, you'd have to manually create the runtime, which is more boilerplate. Inside main, we build a router. The router is your central hub. It maps URLs to handler functions. We call router new and then chain route calls. Think of the router like a phone switchboard. When a request comes in, the router looks at the number, the URL, and connects it to the right handler. For the route path / we use get and pass the hello handler. For /hello, same pattern. For /health, we have a health check endpoint. Each route method takes two things, the path pattern and the handler function. Let's look at the handlers. The hello function is beautifully simple. Async fn, hello arrow ampersand static stock. It just returns a string literal. That's a valid Axum handler. No macros, no annotations, just a function. This is one of Axum's strengths. Handlers are just functions. You can test them in isolation. You can compose them. You can reuse them. There's no framework magic hiding behavior. Compare this to some other frameworks where handlers are methods on classes with decorators and inheritance. Axum keeps it simple, functions that take inputs and return outputs. Axum is flexible about return types. You can return a static string slice, a own string, a tuple with status code, JSON data, HTML, or even implement your own into response trait. Let me break this down because it's important. The hello handler returns ampersand static stir, that's a string baked into the binary. 0 allocation, maximum performance. The compiler knows the string at compile time. The health handler returns a tuple of status code and a string. This sets the HTTP status explicitly. Without this, Axum defaults to 200 OK. But sometimes you want 201 created, or 204 no content. Tuples let you control that. Why does this work? Because Axum has a trait called into response. Anything that implements into response can be a handler return type. Strings implemented, tuples implemented, jubels implemented, JSON wrappers implemented, and you can implement it for your own types. This is Rust's trait system at work, extensibility without inheritance. After building the router, we create a TP listener bound to port 3000. The wait keyword here, we're waiting for the OS to give us the port. This might fail. What if port 3000 is already in use? That's why we have the expect call. It provides a helpful error message if binding fails. Then we call Axum serve with the listener and router and await it. That's the entire server setup. 3 lines, build router, bind listener, serve. Clean and simple. Let me emphasize how simple this is compared to old Rust web development. Before Axum, you might need 100 lines just to set up a basic server. Now it's 3. The server blocks here, listening forever until you hit Ctrl+C. That's what the await does. It keeps running, handling requests, until you stop it. Let's run it. In your terminal, cargo run-p, module 01, intro. The first time, cargo downloads and compiles dependencies. This takes a minute. Subsequent runs are fast because everything is cached. The server starts on localhost 3000. Open a new terminal and curl localhost 3000. You see, hello, world from Axum. Try curl localhost 3000/health. You get OK with a 200 status. Try curl localhost 3000/non-existent. You get a 404, not found. Axum handles this automatically when no route matches. Congratulations, you just built a web server in Rust. It took maybe 30 lines of code, and it's fast, really fast. We're talking thousands of requests per second on modest hardware. Let me explain why async matters here. This is crucial for understanding web development in Rust. When a request comes in, the handler runs. If that handler does I/O database queries, file reads, API calls, it waits. In a traditional thread per request model, that thread is blocked, just sitting there, doing nothing, using memory. With async, when we await an I/O operation, Tokio can schedule other tasks. While waiting for a database, we can handle other requests. One thread can manage thousands of connections. Think of it like a restaurant. In the thread per request model, each waiter serves one table at a time. Even when waiting for food from the kitchen, they just stand there. In async, one waiter serves multiple tables. While waiting for one table's food, they take another table's order. Much more efficient. This is why Rust web servers are so fast. Axum is built on Tokio and hyper-battle-tested async infrastructure that's been refined for years. Let me save you some debugging time. Here are common mistakes beginners make. First, forgetting the Tokio main attribute. You'll get an error about await being used outside an async context. Add the attribute. Second, binding to a port that's already in use. You'll see, address already in use. Either stop the other process or use a different port. Third, forgetting await on serve. Your server will start but immediately exit because nothing is waiting for it. Fourth, running cargo run from the wrong directory. Make sure you're in the workspace root, or use -p to specify the package. Let me give you a mental model of what happens when a request arrives. The TP listener accepts a connection. The HTTP library parses the raw bytes into an HTTP request. Axum's router matches the path and method to a handler. Extractors pull data from the request. Your handler runs. The return value is converted to a response via into-response. Hyper sends the bytes back to the client. All of this happens asynchronously. Multiple requests can be in flight simultaneously. One might be waiting for database I/O while another is running its handler. Module 1 teaches you, Axum uses async await and requires Tokio. The Tokio main attribute sets up the runtime. Router is the central routing hub. It maps paths and methods to handlers. Handlers are normal async functions. No magic, just functions. Return types are flexible strings, tuples, JSON, whatever. Anything implementing into-response works. The serve function is the new Axum 0.8 way to run servers. Clean and simple. This is the foundation. Everything else builds on this. Make sure you understand these concepts before moving forward. Module 2 is where routing gets interesting. We learn the new path syntax, wildcards, query parameters, and router nesting. This module is critical because routing is what makes REST APIs work. Get it wrong and your API is a mess. Get it right and it's a joy to use. Open module 02 routing/src/main.rs. The first thing I want you to see is line 29, the getUser handler with path extractor. The route is defined with /user/open brace ID close brace. See those curly braces? That's the Neo Axum 0.8 syntax. In old tutorials, you'll see :id. Don't use that anymore. It still works but it's deprecated. Curly braces are the future, and they're more readable. The handler signature is async fn getUser, open paren, path open paren 8 close paren :path angle bracket u64, angle bracket close paren. That's a lot of punctuation, so let me break it down. Path is an extractor. It extracts data from the request path. The inner id is the destructured value. The angle bracket u64 tells Axum to parse the path segment as an unsigned 64-bit integer. If someone requests /user/123, the id variable equals 123. Automatic parsing, automatic type checking. What about multiple parameters? Look at line 34, the getUser boast handler. The route is /user/open brace user remis ulza close brace /posts /open brace post unca close brace .c. The handler uses path with a tuple, path open parens user ID, post ID close paren path angle bracket open parens u64, u64 close paren angle bracket. Axum extracts both values in order. First segment goes to user ist, second to post ID. Type safe, compile time checked. For complex paths, use a struct. Look at line 39, the post path struct with user ID. Post underscatus aid and comment underscatus. The handler takes path of post path. This is cleaner for many parameters. You get named fields instead of tuple indices. The struct must derive deserialize because Axum uses serde under the hood. Line 60 shows wildcard routes. The path is /files/open brace * path close brace. The asterisk means capture everything that follows. Request /files/docs/readme.md. The path variable is doc/readme.md. This is perfect for file servers, catch-all routes, or serving static content. Just remember wildcards are greedy, so put them after specific routes. Line 74 shows query parameters with the query extractor. We define a pagination struct with page and limit as option U32. Optional fields don't require the query parameter to be present. The handler takes query of pagination. For a request like /items $page equals 2 ampersand limit equals 20, those values are automatically extracted and parsed. Defaults come from unwrap OSDS, or, if page isn't provided, we default to 1. Clean handling of optional parameters. Look at the HTTP methods section starting at line 183. We have routes for JATE, POST, PUT, patch and delete on the same resource. For /resource, we use get and post. For /resource/open brace /ite, close brace, we chain get, put, patch and delete. Each HTTP method has its own function in the routing module. You can chain them on the same path. This is proper REST API design. 1 resource, multiple operations. Line 122 shows router nesting with the user WR routes function. It returns a router with routes for /and/ed. In main, we nest this router under /API/v1/users. Now /API/v1/users/123 routes to the nested handler. Nesting is powerful for organizing large APIs. Group user routes, post routes, admin routes each in their own router nested under appropriate paths. You can also merge routers. The API under sector v1 nests user sector routes and post under sector routes. Then API under sector v1 routes is nested under /API/v1. For version APIs, you might have API under sector v1 routes, each merged into the main router. Clean separation without code duplication. Finally, fallback routes. Line 199 shows .fallback with a not /wonderfound handler. When no route matches, the fallback handler runs. Return a 404 status with a friendly message instead of a cryptic error. Always add a fallback. Users deserve clear feedback when they hit wrong URLs. Module 2 teaches you new curly brace syntax for path parameters. Path extractor with tuples or structs. Wildcards with asterisk for catch-all routes. Query extractor for URL parameters. Router nesting and merging for organization. Fallback for unmatched routes. Master routing and your APIs become intuitive. Extractors are Axum superpower. They pull data from requests paths, query strings, headers, JSON bodies and convert them to typed Rust values. Module 3 explores built-in extractors and teaches you to build custom ones. Think of extractors as plugins for your handlers. Each extractor knows how to read a specific part of the request. Path reads URL segments. Query reads query strings. JSON reads JSON bodies. Header map gives you all headers. You combine them by listing multiple parameters in your handler. Axum runs each extractor in order. Line 27 shows the JSON extractor. The createUser struct has name and email fields, both strings. The handler takes JSON of createUser. When a post request comes in with a JSON body, Axum parses it into your struct automatically. If parsing fails, malform JSON, wrong types, missing required fields, Axum returns a 422 unprocessable entity error. You don't need validation code. The type system handles it. Line 35 shows header map extraction. The handler takes headers:\header map and can access any header. Get the content type with headers.get of content type. Get authentication with headers.get of authorization. Full access to everything the client sent. For specific headers, you can extract just what you need. Line 40 shows extracting a single host header. Sometimes you need raw bytes. The bytes extractor gives you the body as a byte buffer. This is useful for file uploads, binary protocols, or when you need to compute a hash of the body. No parsing, just raw data. Here's something critical. Extractor order matters. Body-consuming extractors like JSON and bytes read the entire request body. Once consumed, it's gone. You can't use 2 body extractors in the same handler. Non-consuming extractors like path, query, and header map can be in any order. Put body extractors last. If you mess this up, you'll get cryptic errors about the body already being consumed. Now you know why. Line 50 shows custom extractors. This is a BIDT change from old Axum versions. We define an API key struct that holds a string. We implement from request parts for it. This trait lets Axum use it as an extractor. In old Axum, you needed the async.trait macro. Not anymore. Rust now supports native async traits. Look at line 60, just async, fn from 16c.traits, no macros. The implementation reads the x-API key header. If found, return the API key header. If missing, return 401 unauthorized. Now any handler can take API key as a parameter. Line 80 shows a protected endpoint. If the header is missing, Axum runs your rejection logic before the handler even executes. Security at the extractor level, no boilerplate in every handler. This pattern is incredibly powerful. You can build extractors for authentication, rate limiting, request validation, anything you check repeatedly. The state extractor deserves its own module, but let's preview it. State holds shared application state database connections, configuration, caches. We'll cover this deeply in Module 5. For now, know that state is an extractor like any other. What if an extractor might not have data? Use option. Option of query, option of header. If the data doesn't exist, you get none instead of an error. This is perfect for optional query parameters or headers that may or may not be present. Handlers can take many extractors. Look at line 95, we have state, path, query, and JSON all in one handler. Axum extracts each in order. State first, then path, then query, finally JSON. All strongly typed, all validated, all before your code runs. This is composition at its finest. Each extractor does one job well. Combine them for complex behaviors. Module 3 teaches you built-in extractors: path, query, JSON, headers, bytes. Extractor ordering body consumers go last. Custom extractors without async W8 native async in 0.8. Optional extractors with option. Combining extractors with option. Combining extractors for complex handlers. Extractors are your data entry point. Master them and your handlers become clean and focused. We've learned how to get data into handlers. Now let's learn how to send data out. Module 4 covers response types: strings, JSON, HTML, custom headers, redirects, and implementing your own into response. The simplest response is a string. Return ampersand static Stein. Axum sends it with a 200 OK and text slain content type. Return a string, same thing but allocated. Return an empty tuple 204, no content. Return status code, just the status, empty body. Axum is incredibly flexible here. For JSON, wrap your data in the JSON type. Line 25 shows JSON of a user struct. The user struct derives serialize. When you return JSON of user, Axum serializes it, sets content type to application/JSON, and sends it. For API development, this is your bread and butter. Structured data in, structured data out. Line 40 shows HTML responses with the HTML responses with the HTML type from Axum response. Return HTML of a string and Axum sets content type to text HTML. You can embed entire HTML pages, use template engines, whatever you need. This is great for admin dashboards, landing pages, or hybrid applications. What if you need a custom status code? Return a tuple. Line 50 shows open paren status code C100 created, JSON of user close paren. The tuple sets the status to 200 ferv1 and returns JSON. For custom headers, add a header array to the tuple. Line 60 shows setting X custom header. You can set any header you want. Line 70 shows redirects with the redirect pipe. Return redirect permanent to /new location for a 329 for a 31 redirect. Return redirect temporary for 307. Redirect to for 303. Use these for moved resources, login redirects, or post-submit redirects. Here's where it gets powerful. The into-response trait lets you define custom response types. Line 80 shows an API response struct that wraps any data with success status, a message, and the payload. We implement into response for API response. The into _detecels was bias, we set the status, serialize to JSON, and return. Now any handler can return AB response, consistent response format across your entire API. Handlers can return result. If out Axum uses the success type. If error Axum uses the error type. Line 100 shows result of JSON user, app error. On success, return user data. On error, return your custom error type. The error type must implement into response. We'll dive deeper in Module 7 on error handling. Let me give you practical guidance. For APIs, use JSON. For web pages, use JSON. For web pages, use HTML. For files, use bytes with appropriate headers. For redirects, use redirect. For streaming, use server-sent events or WebSockets. We'll cover those in Module 10. For complex applications, build custom response types that standardize your API format. Module 4 teaches you simple return strings, status codes, JSON and HTML wrappers, tuples for status plus body plus headers, redirects with the redirect type, custom into response for consistent APIs, result returns for fallible handlers. Your responses shape the API experience, make them consistent and meaningful. Real applications need shared state database pools, configuration, caches, counters. Module 5 teaches you to manage state in Axum. The primary way to share state is the state extractor. Look at line 29. The handler takes state of archive and config, state wraps your data type. You pass the state when building the router with Wi-Fi tower state. Line 23 shows app config app-name, version, maxuster items sexture pasta ul, pver capture page. This configuration doesn't change at runtime. We wrap it in Arc atomic reference counting. Arc lets multiple handlers share the same data without cloning it. It's thread safe and nearly free. When you call with Dusted with an Arc, all handlers can access the same configuration, memory efficient and safe. What about state that changes? Line 62 shows a todo store arc of a rule lock of hashmap. Rule lock is a read-write lock. Multiple readers can access simultaneously. Writers get exclusive access. The create todo handler calls store.write.unwrap and inserts a to-do. The list under todo handler calls store.read.unwrap and iterates. This pattern is perfect for in-memory caches, counters, or any data that handlers modify. Why row lock instead of mutex? Performance. Mutex gives exclusive access for all operations. With a read-heavy workload which most web apps or readers block each other unnecessarily. Row locks a current reads. Only writes need exclusivity. For web applications, reads vastly outnumber writes, so raw lock is usually better. Large applications need multiple state types. Line 140 shows combined state with config, to-dos and metrics all in one struct. Implement clone for the struct. Each arc inside clones cheaply just incrementing a counter. Pass combined state to with understate to state. Handlers can access any field they need. Line 172 shows the DB pool pattern. In real apps, this would be SQLx PG pool or similar. Connection pools are inherently shareable, that's their purpose. Pass the pool as state and handlers can query as needed. We'll see real database integration in Module 8. For now, understand that pools are just another state type. Line 208 shows the extension pattern. Extensions are request scoped state different per request, set by middleware. Common use, authentication middleware validates a token and inserts current user into extensions. Handlers extract it knowing the user is authenticated. Use state for app-wide data. Use extension for request-specific data. Here are my recommendations. Keep state lean. Don't stuff everything in one struct. Group-related data. Use Arc for sharing. It's cheap and safe. Prefer Ralloc over Mutex for web apps. Initialize state before building the router. Errors at startup are easier to debug than errors during requests. Consider separate routers for different state needs. Merge them at the end. Module 5 teaches you state extractor for accessing shared data. Arc for immutable sharing. Aarambh for mutable sharing. Combine state structs for multiple types. Extension for request, scope data. Database pools as state. State management is the backbone of real applications. Middleware runs before or after your handlers. Logging, authentication, compression, cores SAOS, Nijai. Ppois Vasm uses Towers layer system. Module 6 teaches you to use built-in middleware and build custom ones. Tower is the service layer used by Axum. A layer wraps a service to add behavior. Think of layers as an onion. Request enters, passes through each layer, hits the handler, response passes back through the layers. Each layer can modify request or response. Line 77 shows course layer from Tower HTTP. We configure allowed origins, methods, and headers. Then we add the layer to the router. Chorus is essential for web APIs accessed from browsers. Without it, JavaScript can't call your API from different domains. Compression layer automatically compresses responses. Browser send except encoding gzip, your server responds with compressed data. Free bandwidth savings. Just add the layer. Trace layer from Tower HTTP integrates with the tracing library. It logs every request method, path, status code, duration. This is not optional in production. You need visibility into what your server is doing. Trace layer gives you that with zero effort. Line 31 shows custom middleware using middleware from _scatter, quote, the logging _scatter middleware function takes request and next. Capture the method and URI. Call next.run request.await. Log with the response status. This is the pattern, do something before, call next, do something after. The function's signature is async fn taking request and next, returning response. Line 48 shows timing middleware. It records start time, calls next, calculates duration, and sets an X response time header. Clients can see how long requests took. Great for debugging and SLA monitoring. Line 60 shows authentication middleware. This is more interesting because it can reject requests. We read the XAP header. If it matches our secret, we continue. If not, we return 401 unauthorized immediately. The handler never runs. The return type is result of response, status code. Returning error short-circuits the request. Not all routes need all middleware. Line 114 shows route layer. We create a protected router with specific routes. We add auth quarters middleware with route layer. Only those routes require authentication. Then we nest the protected router into the main app. Public routes remain public. Protected routes are protected. Clean separation. Layer order matters. Layers apply in reverse order. The last layer added runs first. If you add logging then authentication, requests hit authentication first, then logging. Think about it. You want to log everything, including rejected requests, so logging should be outermost. In code, add logging last, so it runs first. Line 127 shows Service Builder for applying multiple layers cleanly. Service Builder new, chain layer calls, pass to the router's layer method. It reads top to bottom, applies bottom to top. Same rules. Here's a typical middleware stack. Outermost, trace layer for logging. Next, compression layer. Next, timeout layer if you have one. Next, CORS layer. Innermost, authentication for protected routes. This order ensures logging sees everything, compression happens on all responses, and auth runs close to handlers. Module 6 teaches you towers layer concept and units of behavior, built-in middleware, CORS, compression, tracing, custom middleware with from _scaft and boss, route-specific middleware with route-layer, layer ordering last added runs first. Service Builder for clean composition. Middleware is your cross-cutting concern solution. Errors happen. Networks fail, data is invalid, resources don't exist. How you handle errors defines your API's quality. Module 7 teaches professional error handling in Axum. First rule, never panic in handlers. Panics crash threads and cause poor user experience. Use result. Return errors, don't panic on them. Line 23 shows app error enum with this error derive. We define variants, user not found with an ID, invalid input with a message, database error, unauthorized, internal. The error macro on each variant generates the display trait automatically. User not found displays as user not found, 123. Line 51 implements into response for app error. We match on the error variant, user not found returns 404, invalid input returns 404, unauthorized returns 401, database and internal return 500. We create an error response struct with error message and status code. Return it as JSON. Now any handler returning result with app error gets proper error responses automatically. Line 80 shows a handler returning result of JSON user, app error. We look up a user. If found, return OCOF of JSON of user. If not, return error of app error user not found. The question mark operator works beautifully here. If a function returns an error, question mark propagates it. No verbose match statements. Line 114 shows a complex handler with chained fallible operations. We call find user with question mark. We call validate user with question mark. Both can fail. Either failure returns early with the appropriate error. This is Rust's power explicit error handling without boilerplate. For debugging, add context errors. Use anyhow context or with unsa context methods. Instead of connection failed, say failed to connect to database at localhost 5432. Context helps you debug. Your API consumers aren't reading your code. Error messages must be clear. Instead of ENOENT, write, the requested user was not found. Instead of parse error, Right, the mail field must be a valid email address. Clear errors reduce support tickets. Always log errors for debugging. Use tracing error macro with the error. Your users see a friendly message. Your logs have the full stack trace. Both purposes served. Module 7 teaches you custom error types with this error. Into response for automatic error responses. Result-based handlers. Question mark for propagation. Context for debugging. Clear messages for UGing. Error handling is UX. Make it good. Time for real persistence. Module 8 connects Axum to PostgreSQL using SQLx. This is where your application becomes real data that survives restarts. Up until now, we'd been using in-memory hash maps. That works for demos, but production applications need persistent storage. PostgreSQL is battle-tested, open source, and works beautifully with Rust. SQLx is a Rust library for SQL databases. It's async native, compile time checked, and type safe. But why choose it over alternatives like Diesel or Aarambh? First, compile time query checking. SQLx verifies your queries against the actual database schema. Typos in column names, caught at compile time. Wrong types, caught at compile time. Wrong types, caught at compile time. Queries that don't match your schema, caught at compile time. Second, it's async from the ground up. Other ORMs were retrofitted for async. SQLx was designed for it. Third, you write real SQL. No DSL to learn. If you know SQL, you know SQLx. Fourth, no code generation required. Diesel needs Diesel CLI. SQLx works with just cargo build. This is a game changer for correctness and developer experience. You need PostgreSQL running. The easiest way is Docker. One command and you're done. Run docker run -d -name postgres -e postgres urgesgres gort equals postgres-p5432:5432 postgres. Let me break that down. -d runs in detached mode background. -name gives it a name so you can stop it later. -e sets the password environment variable. -p maps port 5432 from container to your machine. That starts PostgreSQL on localhost 5432. Now set your environment variable. On Linux or Mac, export database ULL equals postgres:/postgres:/postgres at localhost/axum weges at localhost/axum peachertov. Create the database, PSQL-H, localhost-U, postgres-create, database ACH-erate kate abas ace on source course. You're ready, let's connect. Line 35 shows creating a PH pool. This is crucial to understand. Opening a database connection takes time. TCP handshake, authentication, protocol negotiation. If you open a connection for every request, your server is slow. Connection pools solve this. They open connections once and reuse them. PG pool options new, set max ICE actions to 5, and call connect with the database URL. The pool manages everything. When a handler needs a connection, it borrows one. When done, it returns it to the pool. Fast, efficient, zero connection overhead per request. Pass the pool as state to your router. Every handler can access it. All handlers share the same pool. One important note, don't set max ICH connections too high. Each connection uses server memory. 5 to 20 connections handle most workloads. Only increase if you prove you need more. Line 25 shows the user struct with SQLx, derived from row. This is mapping magic. Fields are ID as UUI, name and email as string, created duskuat as chrono date time. From row let SQLx convert database rows to your struct automatically. Column names match field names. PostgreSQL returns columns, SQLx maps them to struct fields. If column names differ, use the SQLx rename attribute. If a column is nullable, make the field option. SQLx handles it all. Notice we're using UOED for the primary key. UUIDs are better than auto-increment integers for distributed systems, no coordination needed between servers, and they're unpredictable, which is better for security. Line 70 shows a basic query, SQLx query us angle bracket user. The SQL is select star from users. We call fetch us call with the pool. This returns a vec of user, all rows, fully typed. Each row becomes a user struct. For a single row, use fetch unger1. This is for queries that must return exactly one row. If 0 or multiple rows, it errors. For optional, use fetch unger1. This returns option user. None if no rows, some if found. Use this for lookups by ID. For just one row when multiple exist, use fetch ushter1. It fails if 0 rows. Use fetch ushter1 to handle not found gracefully. Line 85 shows parameterized queries for finding one user. This is critical for security. The SQL is select star from users where id equals $1. We call bind with the EID. Then fetch actual. The $1 is a placeholder. Bind fills it in. This prevents SQL injection, the most common web vulnerability. Let me explain SQL injection. If you concatenate user input into SQL, attackers can manipulate your queries. Input like dropable users can destroy your data. Parameterized queries prevent this. The database knows what's SQL and what's data. Data is never executed as SQL. Never concatenate user input into SQL strings. Always use bind. This is non-negotiable. Line 100 shows inserting users. The SQL is insert into users open parent id name, email close parent values $1, $2, $3 working star. Rebind the id, name, and email. Each bind corresponds to a placeholder. Order matters. Returning star is PostgreSQL specific but incredibly useful. It gives us the inserted row back so we can return it to the client. No need for a separate select. The handler generates a UUID for the id, binds all values, and returns the created user as JSON. Status 201 created tells clients the resource was created. Updates follow the same pattern. SQL with placeholders, bind values, execute or fetch. Update users set name equals $1, email equals $2 where ID equals $3. Bind the new values and the it. The execute method returns the number of affected rows. Check if 0 rows affected, that means the resource didn't exist. Return 404, not found. If you need the updated row, use returning star again and fetch instead of execute. SQLx returns result types. Every database operation can fail. Map SQLx error to your app error. What kind of errors? Connection errors, database is down. Timeout errors, query took too long. Constraint violations, unique key conflict, foreign key missing. Not found for fetch core 1 when 0 rows, handle each appropriately. Constraint violations might be 400 bad request user provided invalid data. Not found is 404. Connection issues are 500, not the user's fault. Use match or if let to distinguish error types. Lob the full error for debugging, return a friendly message to users. For multiple operations that must succeed together, use transactions. Either all succeed or all fail. Classic example, transfer money between accounts. Debit 1, credit another. If credit fails, debit must roll back. Call pool.begin.await for a transaction. Make your queries. Call transaction.commit.await. If anything fails before commit, the transaction rolls back automatically when dropped. Atomicity guaranteed. Use ampersand transaction in your queries instead of ampersand pool. The transaction tracks which connection to use. I should mention migrations. We haven't covered running them, but you need to create tables. Create a migrations folder. Put SQL files there. Run SQLx migrate run. SQLx tracks which migrations have run. It won't rerun migrations. Save for production. For this course, you can run the create table manually. But production apps should use migrations. A few tips for production database work. Use select only the columns you need. Select star is convenient but wasteful if you only need 2 columns. Add indexes on columns you filter or sort by. Without indexes, PostgreSQL scans the entire table. Use explain analyze to understand query performance. Look for sequential scans on large tables. Monitor connection pool usage. If you're waiting for connections, increase pool size or optimize slow queries. Module 8 teaches you SQLx for async, type-safe database access, compile time query verification catches bugs early. Connection pooling for efficiency. Reuse connections instead of opening new ones, from row for automatic mapping. Database rows become Rust structs. Parameterized queries to prevent SQL injection. Never concatenate user input. CRUD operations create, read, update, delete. The foundation of any API. Error mapping for user-friendly responses. Hide technical details, provide helpful messages. Transactions for atomicity. Multiple operations succeed or fail together. Databases make applications real. This is where data persists. Module 9 adds security JWT tokens, password hashing, protected routes, and role-based access. This is where your API goes from open to secure. Authentication answers one question. WHO is making this request. Authorization answers another. What are they allowed to do? We cover both in this module. Get security wrong and you're on the news for all the wrong reasons. Get it right and your users can trust you with their data. JSON Web Tokens are a standard for stateless authentication. Let me explain why this matters. Traditional session authentication works like this. User logs in, server creates session, stores it in memory or database, gives user a session ID cookie. Every request, server looks up the session to know who's asking. The problem? Sessions are stateful. Server needs to remember them. If you have multiple servers, you need shared session storage. Scaling is complex. JWT is different. The server issues a signed token containing user information. The token itself contains everything needed to verify the user. Server doesn't store anything. No server-side sessions. Add more servers without coordination. Horizontal scaling is trivial. Perfect for APIs and microservices. A JWT has three parts separated by dots: header, payload, and signature. The header says which algorithm signs the token, usually HS256 or RS256. The payload contains claims user ID, role, expiration time. The signature verifies the token wasn't tampered with. Anyone can decode the payload, it's just base 64, but only the server can create valid signatures because only the server knows the secret. If someone modifies the payload, the signature won't match. The server rejects it. Tamper-proof by design. Never store plain passwords. I cannot stress this enough. If your database leaks, attackers have everyone's password. Users reuse passwords across sites, so attackers can access email, banking, everything. Line 72 shows hashing with Argon 2. Argon 2 won the password hashing competition in 2015. It's memory hard, meaning GPU attacks are expensive. It's the current gold standard. The hash #per function generates a random salt unique per password. The salt prevents rainbow table attacks. Then it hashes the password with the salt, store the resulting hash string. The hash is one way. You cannot recover the original password from it. That's the point. Line 81 shows verification. When a user logs in, you don't decrypt their stored hash, you can't. Instead, you hash the provided password with the same salt and compare results. Parse the stored hash, it contains the salt. Hash the provided password with that salt, compare. If they match, authentication succeeds. If not, it fails. Never tell users which part failed. Invalid email or password is correct. Invalid email or password is correct. Invalid password tells attackers the email exists. Line 36 shows the claim struct. Claims are statements about the user embedded in the token. The subclaim is the subject, typically the user ID. The X-claim is expiration, a Unix timestamp when the token becomes invalid. The role claim stores authorization level, user, admin, whatever. You can add custom claims, but keep tokens small. They're sent with every request. Store user details in the database, not the token. Line 93 shows token creation with the JSON Web Token crate. We build claims with user ID, expiration 24 hours from now, and role. The chrono crate calculates the timestamp. We call encode with the default header, claims, and secret key. The secret must be kept secret. Use environment variables. Generate a long random string, at least 32 characters. Never hardcode secrets. Never hardcode secrets. Never commit them to Git. In production, consider token refresh flows. Short-lived access tokens, 15 minutes with longer-lived refresh tokens. If a token leaks, the blast radius is limited. Line 108 shows verification. Every protected request verifies the token. Call decode with the token, secret key, and validation options. Validation checks expiration automatically. If verification succeeds, we get the claims. If the token is expired, return 401. If tampered, return 401. If missing, return 401. The claims tell us who the user is and what they can do. Insert this into request extensions for handlers to use. Line 165 shows authentication middleware. This is the gatekeeper. We extract the authorization header. Format is bearer token string here. We strip the bearer token string here. We strip the bearer prefix to get the raw token. We verify it. If valid, we create a current user struct from claims. We insert it into request extensions. Extensions are request scoped storage middleware can write, handlers can read. If any step fails, no header, wrong format, invalid token, return 401 unauthorized immediately. The handler never runs. Security at the edge. Line 199 shows protected route setup. We create a router with protected handlers, /me returns user info, /admin requires admin role. We add auth middleware with route _/ layer. Only these routes require authentication. We nest /protected. Now post/login, public, returns token G8 /protected /me, requires valid token G8 /protected /admin, requires token with admin role, clean separation. Public routes stay public, protected routes check tokens. Line 130 shows the login handler. This is where tokens are born. We receive email and password as JSON. In a real app, we query the database for the user. We verify their password hash with Argon 2. If credentials are valid, create a token with their ID and role. Return it as JSON with expiration info. If invalid, return 401. Don't say why it failed, just invalid credentials. In this example, we use hard-coded credentials for demonstration test at example.com with password 123. In production, always check the database. Line 154 shows role checking in a handler. Authentication is who you are. Authorization is what you can do. We get current user from extensions. The middleware already verified the token. Check the role field. If not admin, return 403 forbidden. For more complex scenarios, build permission extractors. Check multiple roles, specific permissions, resource ownership. But the pattern is the same. Check in middleware or early in handlers. Let me save you from some common security mistakes. Storing JWTs in local storage is dangerous. XSS attacks can steal them. HTTP-only cookies are safer. Not checking token expiration. Always validate xplaim. Using weak secrets. Generate with a cryptographically secure random generator, not using HTTPS. Tokens in transit can be intercepted. No rate limiting on login. Brute force attacks try thousands of passwords. Store secrets in environment variables, never in code. Use HTTPS everywhere. Let's encrypt is free. Set reasonable token expiration 24 hours for access tokens, 7 days for refresh tokens. Implement token refresh for better UX without long-lived tokens. Rate limit login attempts 5 per minute per IP. Log authentication events, successful logins, failed attempts, token refreshes. Consider multi-factor authentication for high-value applications. Module 9 teaches you JWT for stateless authentication. Tokens contain claims, signatures prevent tampering. Argon 2 for password hashing. Never store plain passwords, ever. Token creation and verification with the JSON Web Token Crate. Auth middleware that gates protected routes. Invalid tokens never reach handlers. Protected routes set up with route _layer, public and private routes coexist. Role-based access control. Who you are versus what you can do. Security is your responsibility. Users trust you with their data. Module 10 goes beyond basic HTTP WebSockets for real-time communication, server-sent events for streaming, file uploads, and static file serving. These features transform your API from request response into a living, real-time system. Chat apps, live dashboards, collaborative tools. This is where they're built. WebSockets are bidirectional communication channels. Unlike HTTP's request-response pattern, WebSockets stay open. Both client and server can send messages anytime. HTTP is like sending letters. You write, send, wait for a reply. WebSocket is like a phone call. Once connected, both parties can talk whenever they want. Chat apps, live updates, multiplayer games, collaborative editing, all WebSocket territory. Anywhere you need instant communication. Line 30 shows the WebSocket handler. It's different from regular handlers. The handler takes WebSocket upgrade extractor. This is special. It tells Axum this endpoint handles WebSocket upgrades. We call on _upgrade with a closure that handles the socket. This upgrades the HTTP connection to WebSocket protocol. The closure runs in a separate Tokio task handling messages. The upgrade is automatic. Client sends upgrade request. Axum does the protocol switch. Your closure runs for the lifetime of the connection. Line 40 shows the socket handler in detail. We loop with while let sum of msg equals socket.recv.await. This reads messages as they arrive. For each message, we match on the type. Text messages contain strings, chat messages, JSON commands, whatever. We echo them back with a prefix. Binary messages are raw bytes file chunks, images, audio streams. Handle them as your use case requires. Ping messages are connection health checks. Axum handles PONG responses automatically. Close messages end the connection cleanly. This is an echo server symbol but demonstrates the pattern. Real apps would parse messages, update state, broadcast to other connections. For chat apps, you need to broadcast messages to all connected clients. The pattern: store all connections in shared state arc of RO lock of vec of socket senders. When a message arrives, iterate through and send to each. Use Tokio broadcast or Tokio watch channels for efficient fan-out. These are built for one-to-many communication. We don't implement this in the module, but the pattern is straightforward once you understand individual connection handling. SSE is simpler than WebSocket's one-way streaming from server to client. The server pushes, the client receives. Perfect for live feeds, notifications, progress updates, stock tickers. Anywhere the server has data to push and the client just listens. Line 55 shows the SSE handler. Return C of a stream. Each item becomes an event sent to the client. The client keeps the connection open and receives updates in real time. Browser support is excellent. Event source API is simple, just pointed at your endpoint. The stream uses Tokio as a stream's repeat as in throttle. We generate an event every second with a current timestamp. The repeat as in throttle with closure runs infinitely. Throttle adds a delay between items. Each event has an event type, data, and optional ID. Clients can filter by event type. Keep alive is crucial. It prevents connection timeouts from proxies and load balancers. Periodic empty messages keep the connection alive. Line 75 shows file upload handling. This is how users send files to your server. The handler takes multi-part extractor. Multi-part is the standard for form uploads. Each file is a part in the request. We loop through fields with while let sum of field equals multipart.next_field.await. Each iteration gives us one uploaded file. Each field has metadata: name from the form, file name from the user's computer, content type like image/png, call bytes to read the file data. For large files, use streaming to avoid loading everything into memory. Save to disk with Tokio FS write. Generate unique file names to avoid conflicts. Validate content types for security. For production, configure body limits. Use default body limit layer to set maximum request size. 10 MB is reasonable for most apps. Huge uploads can exhaust memory or fill your disk. Set limits based on your use case. Validate file types. Don't trust content type headers, attackers can fake them. Check magic bytes or scan files. Store uploads outside your web root. Never serve user-uploaded files directly, they could contain scripts. Generate random file names. Don't use user-provided names, path traversal attacks are real. Line 100 shows static file serving with served from tower HTTP, pointed at a directory. It serves any file within. Axum handles proper content types, caching headers, range requests, everything. Nested under a path like /static. Now /static/styles.css serves your CSS file. In production, put a CDN in front, Cloudflare, Aswis CloudFront, or similar. They cache files globally for fast delivery. Real apps combine these features. Serve static HTML that opens a WebSocket. Stream updates via SSE while accepting file uploads. Axum handles all of it cleanly. Each feature is just another route or router merged into your app. The same patterns apply. Line 20 shows an HTML demo page that demonstrates everything. It has buttons to test WebSocket, SSE, and file upload. JavaScript connects and displays results. A self-contained demo for learning. Module 10 teaches you WebSocket upgrade and message handling. Bidirectional real-time communication. Server-sent events for one-way streaming. Push updates to clients. Multi-part file uploads. Handle user-uploaded files safely. Static file serving. Deliver assets efficiently. Combining features in one app. Each is just another router. These features unlock real-time, interactive applications. Module 11 is about confidence. Tests prove your code works. They catch regressions before users do. They document expected behavior better than comments. Untested code is broken code, you just don't know it yet. Every production bug was untested behavior. Axum makes testing delightful. Let's see how. Axum makes testing easy because the router itself is a tower service. We can send requests directly without starting a real server. No port binding, no network, no race conditions, just direct function calls with full type safety. The one-shot method sends a single request and returns the response. fast, isolated, deterministic. This is why Rust web testing is so much better than other languages. No HTTP client mocking, no fake server setup, just call the router. Line 89 shows the test setup pattern we use throughout. Create test state with a helper function test_store returns an empty in-memory store. Pass it to create_app which builds our router. Now we have a router ready for requests. Each test creates its own state. Tests are isolated. No shared mutable state means no flaky tests. All in memory, blazing fast. Your entire test suite runs in seconds. Line 93 shows testing the health endpoint. This is the simplest case. Build a request with the builder pattern. Set URI to /health. Body is empty. Call app.oneShot with the request and await. Assert the status as 200 OK. Extract the body bytes with collect and assert it equals OK. This takes milliseconds. You can run thousands of tests quickly. Line 113 tests user creation, a more realistic case. We set method to post. URI is /users. Add content type header as application/JSON critical for JSON handlers. The body is a JSON string with a name field. Call oneShot. Assert status is 201 created. Parse the response body as JSON using shared JSON. Assert the user's name matches what we sent. This pattern tests the full cycle: request parsing, handler logic, response serialization. Line 136 tests a not found case. Testing errors is just as important as testing success. Request a user with ID 999. Our test store is empty, so the user doesn't exist. Assert we get 404 not found. Test both paths. Your error responses are part of your API contract. Clients depend on them. Common error cases to test: validation failures return 400, missing resources return 404, unauthorized access returns 401, forbidden actions return 403. Line 153 shows pre-populating state for tests that need existing data. Create the store. Insert a user with known ID and data. Pass to create USQArc app. Now tests start with predictable data. Test queries find the user. Updates modify them. Deletes remove them. This pattern is essential for testing anything beyond creation: reads, updates, deletes, list filtering, search. These one-shot tests are integration tests. They test the full request/response cycle. Extractors run, middleware runs, handlers run. For unit tests, test individual functions directly. The honest password function with known inputs, token generation and parsing, query builder methods, both are valuable. Integration tests catch wiring issues, extractors, failing, middleware in wrong order. Unit tests catch logic issues, calculation errors, edge cases. The testing pyramid: many unit tests, some integration tests, few end-to-end tests, fast feedback at the bottom. Run cargo test to execute all tests. Simple and comprehensive. Cargo test-not capture shows println output, useful for debugging. Cargo test /9 runs specific tests matching that name. Cargo test-p module 11 testing tests only that module. Tests run in parallel by default. Don't share mutable state between tests. Use arg-rolock if you must share, but prefer isolated state per test. What to test? Everything that could break. Authentication: valid tokens access resources, invalid tokens are rejected. Authorization: users can only access their own data, admins can access everything. Validation: invalid input returns 400 with helpful messages. Edge cases: empty lists, 0 values, maximum lengths. Error handling: database errors become 500s, not panics. Module 11 teaches you oneShot for sending test requests directly to your router, no network needed. Request builder pattern for constructing test requests, asserting status codes and parsing response bodies. Pre-populated test state for testing reads, updates, and deletes. Integration versus unit testing, both matter. Running tests with cargo efficiently. Tests are insurance. They cost time to write but save time debugging. Pay the premium. Module 12 prepares your app for the real world. Development is easy, production is hard. Graceful shutdown, structured logging, health checks, containerization, these aren't optional. They're the difference between a hobby project and a professional system. Let's make your Axum app production ready. Docker Compose orchestrates multiple services. It's perfect for local development with databases and dependent services. We define Postgres for the database. We define app for our server. The app depends on Postgres. Compose starts them in order. Environment variables configure both services. /URL points to the Postgres container. Run Docker Compose up and everything starts. Database, migrations, app handled. What happens when your server receives SIGTERM? Without graceful shutdown, connections drop, requests fail. Users see errors. With graceful shutdown, the server stops accepting new connections but finishes in-flight requests. Everyone's happy. Kubernetes sends SIGTERM before killing pods. Awesome sends it before stopping instances. Your deploy scripts send it during updates. Handle it gracefully or face angry users. Line 104 shows with under graceful under shutdown, we pass a future that completes when shutdown is requested. The server runs until that future resolves. The serve function now waits for either all connections to close or the shutdown signal. When signal arrives, it stops accepting new connections and waits for existing ones to finish. Clean exit. No dropped requests. Line 1112 shows the shutdown signal handler in detail. We listen for Control-C with Tokio signal Control-C, with Tokio signal for SIGTERM with Tokio signal Unix. We use Tokio select to wait for whichever comes first. When either arrives, we mark the app as not ready. More on this in a moment, then sleep briefly. This gives load balancers time to detect we're draining. Finally, the future completes and the server shuts down. Line 75 sets up tracing with JSON output. This is crucial for production observability. JSON logs are machine parsable. Your log aggregator CloudWatch, Datadog, Splunk, Elastic can index fields automatically. Filter by user ID, search by error type, aggregate by endpoint. Human-readable logs are nice for development. JSON logs are necessary for production. Set rust r lost _ log environment variable to control log levels. Rust.as log info for normal operation. Rust.as log envo debug for troubleshooting. Rust.as log envo warn to reduce noise. Line 42 shows health and readiness endpoints. Every production app needs both. The /health endpoint is the liveness probe, is the process running. Return 200 if yes. If this fails, your orchestrator restarts the pod. The /ready endpoint is the readiness probe. Should traffic be routed here? Return 200 if ready, 53 if not. During shutdown or initialization, the app might be alive but not ready for traffic. Kubernetes, ECS, Nomad. Every orchestrator uses these probes. Get them right. Line 25 shows ready as atomic bool in shared state. It starts true, we're ready to serve. When shutdown begins, we set it false. The readiness endpoint reflects this. Load balancers poll the ready endpoint. When it returns 530, they stop routing traffic. Give them a few seconds to detect this before actually stopping. This enables zero downtime deployments. New instances come up and become ready. Old instances become not ready and drain. Traffic smoothly shifts. Users notice nothing. Production apps should expose metrics, request counts, latencies, error rates. The /metrics endpoint returns JSON with counters. In a real app, integrate with Prometheus. Use the Prometheus crate to expose metrics in the standard format. Metrics power dashboards and alerts. Without them, you're flying blind. The project includes a Docker file using multi-stage builds. First stage, build. Start with Rust, Slem. Install dependencies. Compile with release flag. Second stage, runtime. Start with Debian Slem. Copy just the binary. No Rust toolchain, no source code, no build artifacts. The final image is under 100 MB. Fast to pull across the network. Fast to start. Minimal attack surface. Before deploying, run through this checklist. Graceful shutdown. Does SIGTERM stop the server cleanly? Test with Docker stop. Logging. Are logs in JSON format? Can you see request IDs? Are sensitive data redacted? Health endpoints do health and ready respond correctly? Test during shutdown. Environment variables. Are all secrets in environment, not code? Database rarel, JDABAC, URLL, JWC SIC, SCRAT, no hard coding. TLS, is HTTPS configured? Usually terminate at load balancer, not in app. Rate limiting, is abuse prevention in place? Tower governor or similar. Errors, do internal errors return 500, not stack traces? Check each item. Production is unforgiving. Deploying is not the end, it's the beginning. You need monitoring. log aggregation, ship logs to CloudWatch, Datadog, or Elastic, search, filter, alert, metrics, export to Prometheus, build Grafana dashboards. Watch request latency, error rates, throughput, uptime monitoring, use Pingdom, Uptime Robot, or similar. Know when your app is down before users tell you. Alerting, PagerDuty, OpsGenie, or email. Wake someone up when things break. Module 12 teaches you graceful shutdown with futures. Finish requests before stopping. Structured JSON logging, machine parsable for aggregation, health and readiness probes. Let orchestrators manage your app. The ready flag pattern for zero downtime deployments. Docker multi-stage builds, small secure images. Docker Compose for local development with databases. Production checklist, don't deploy without checking. Production ready means thinking about operations from day one. Your users depend on it. And that's the complete Axum course. Let me recap what we covered. Module 1, Basic Server Setup and Handlers. Module 2, Advanced Routing with the new syntax. Module 3, Extractors for request data. Module 4, Response Types and Into-Response. Module 5, State Management with Arc and Arulock. Module 6, Tower Middleware Integration. Module 7, Professional Error Handling. Module 8, PostgreSQL with SQLx. Module 9, JWT Authentication. Module 10, WebSockets, SSE, and File Handling. Module 11, Testing Strategies. Module 12, Production Deployment. You now have the complete toolkit for building REST web applications. Where do you go from here? Practice by building. Start a side project. A to-do API, a URL shortener, a webhook, receiver, anything. Explore the Axum documentation. There's more we didn't cover: custom extractors, layer ordering nuances, advanced tower patterns. Consider authentication libraries like Axum Extra for session management. Database patterns like Aarambh if you prefer an ORM. Join the Tokio Discord, that's where the Axum community hangs out. If you made it this far, you're serious about Rust. I respect that. Here's what I need from you: drop a comment. What will you build first with Axum? I want to know. Subscribe and turn on notifications. I'm releasing Rust content weekly. Join our Discord. The community is amazing. Questions get answered, projects get reviewed, people learn together. And if this course saved you hours of reading docs and banging your head against errors, buy me a coffee. Every contribution funds more content. Thanks so much for watching. I'm Darshan. Keep building, keep learning, and I'll see you in the next one. Now go write some Rust. Peace.